We're going to look at how we can use a few given values of a function's derivative to approximate the change in the value of the function itself. We're going to start by looking at this idea in the context of position and its derivative velocity. So we're going to be given a few values of velocity and asked to approximate changes in position. So driver Dominique and passenger Parveen set off on a trip along a very straight road at 7 a.m. To amuse herself, Parveen decided to make estimates of readings on the car's odometer by having Dominique call out the speed every few minutes. Parveen's data for the first 20 minutes of the trip is shown in the table. Given the values of the derivative of the position function above, so that's this velocity, estimate Dominique and Parveen's change in position from 7:10 to 7:11. Pause the video and do this for yourself. There are a variety of approaches you could have taken to come up with your estimate. You knew that the travelers were going at 70 miles per hour at 7:10 and at 68 miles per hour at 7:11. What you didn't know, of course, is how fast they were moving at every instant in between those two times. One reasonable choice for estimating is to take the average of those two. So to say, let's just assume that they were traveling at 69 miles per hour, and they did that for 1 minute, which is 1/60th of an hour. And as a decimal, that's 1.15 miles. It's always worth stopping, making sure our answer seems reasonable. If we had been going 60 miles an hour for 1 minute, we would have gone 1 mile. Our velocity is a little higher than 60 miles an hour. Our answer's a little higher than 1 mile. Seems reasonable. For what we're about to do, it's worth taking a look at a geometric interpretation of this estimate. So if we sketch a graph, let's say the horizontal axis is time since 7 o'clock in hours. So we're interested in 10/60ths of an hour after 7 o'clock to 11/60ths of an hour after 7 o'clock. And the speed at the beginning of that interval was 70, and at the end of that interval was 68. And assuming an average speed over that interval of 69 is the same thing as assuming a constant deceleration over that interval, so that our velocity graph looks linear as we move from a velocity of 70 to a velocity of 68. What I'm going to ask you to think about in relation to the answer we just got is the area of this trapezoid. Stop the video and try to recall from the deep recesses of your geometry brain the formula for the area of a trapezoid. The area is 1/2 the sum of the bases times the height. And it's probably worth doing a little color coding here because people often picture a trapezoid turned 90 degrees from the way this one is oriented. So our bases, base 1 and base 2, are these lengths, and our height, the distance between the bases, is this length. All right, so let's go back and look at our previous calculation. 1/2 sum of the bases, which were 68 miles per hour and 70 miles per hour. So base 1 plus base 2 was 68 plus 70, and half of that was 69. So that's our 69 miles per hour. And the height of the trapezoid was 1/60th of an hour. So it's exactly the calculation that we just did. So the area of that trapezoid is 1.15 miles. In other words, the area under our presumed velocity function, we had to make it up, we didn't know exactly what it was, we just knew 2 points, is equal to change in position over that time interval. We're going to now repeat this technique several times with the goal of coming up for an overall estimate of the change in position of Dominique and Parveen from 7 until 7:20. That is, on each of the time intervals between which we know speeds, we will assume a constant acceleration and then look at the area of the trapezoid. And by adding up all those individual trapezoid areas on each subinterval, we can come up with an estimate for the total change in their position. using the available data and making the rash assumption of a constant acceleration over the course of each interval. So we have to make some assumption. Let's just make that one. Approximate the change in position on each interval. Draw the trapezoids whose areas represent these displacement estimates. Okay, so we've got one done. We did this 710 to 711. That was a 1.15 estimated change in position. And if you couldn't recall it a minute ago, take a moment now to see if you can recall the area formula for a trapezoid. Area of a trapezoid is 1/2 the sum of the bases times the height. And it's really helpful to also recognize that that is just the average of the velocities at the left endpoint and the right endpoint of the time interval times the width of the time interval. For the time interval starting at 7:15, give the value of each of these. So look at this time interval and try to fill in these values. Pause and do that. 7:15, that's 15/60ths. And the velocity at that point is 37, so that's base 1. V of 15/60ths, which is 37. B2, right here, is the velocity at 20/60ths, which is 12. The height is the distance between those bases, 15/60ths to 20/60ths, or 5/60ths. And the area of this trapezoid is the average of the function values at the endpoints times the width of the interval. We'll take this opportunity to look at a couple of things you can do with your calculator. We are going to write this 37 plus 12 over 2 exactly how it looks handwritten by using alpha y equals and then this numerator over denominator. And then it gives us a fraction template. This can be useful particularly if you have an expression that's more complicated than this and you're having trouble keeping track of all the parentheses. So we have 37 plus 12, and then we just arrow down over the 2, arrow across, times, and 5/60ths doesn't need parentheses, so I'm not going to mess with that. Now, if I just push enter here, I get the answer as a fraction. Now that's a perfectly fine answer, but I'm going to take this opportunity to show you a couple of other things you can do with the calculator. One is working with an expression you've already used. I can arrow up. There I've selected the 49/24, arrow up again. Let's say I want to redo that. If I wanted a decimal, I could just put a decimal somewhere in that original expression, and then it'll give me a decimal result. The other thing I want to think about here is that I had mentioned earlier that we were going to use all these individual estimates to come up with an overall estimate. And if, for instance, I'm taking the AP exam and want an answer correct to 3 places after the decimal, I don't want to round intermediate answers. So I want to be storing the answers I get as I go along. So let's say I'll store this one in A, this one in B, this one in C, this one in D, this one in E, and this one in F. So this answer I want to store right now, I'm going to store in the letter F. And to do that, I just push the store button down here next to the 1, and I want to store it in F, so alpha F. And now anytime I push alpha F, I'll have that number back. Now that that number is safely stored in my calculator, I'll round it off here, 2.041 or 2. And the units are miles. That came from this, which was in miles per hour, lengths of the bases, and this, which was the width of the base, in hours. And we multiplied them together, giving us miles. So now I should be able to work out the trapezoid's areas for the remaining intervals, and then move on down and answer this last question, E.